In this example, we're going to look at position feedback control for our DC motor model that we have used before. So we're really looking at being able to be given a gain factor here of Kc and find out what the 2% settling time is and the percent overshoot. So this is a question of analysis. We're taking a model and we're grinding through the answers. One correction that I want to make to this is that I said I'm talking here about a velocity transfer function. It's actually a position because our output here is not n omega, but the output here is theta s. So the first thing we want to do is come up with our closed loop transfer function. So one thing I'm going to recognize here is I've got two blocks which are in series with each other. So this is equivalent to a single block, which I'll call that the open loop transfer function of GOL. So if I first look at the case of without feedback, let's say that we disconnect our feedback loop, and without the feedback we've got GOL, our output of theta, input of a reference position there of theta r. So therefore our open loop transfer function, that's just equal to the multiplication of those two blocks. So that's Kc times our plant transfer function. And our plant transfer function was given by 3 divided by s times s plus 6. Okay. Now with feedback. With feedback, we look back at our original block diagram above, and we see here that the output, theta s, is equal to a transfer function, our open loop one, GOL, where the input here is the difference between our desired, our reference position, theta r, and our actual position there of theta. And so what I do is I bring my thetas both on the left-hand side, and I get a 1 plus G open loop times our output is equal to G open loop times our input here of theta r. So from this we get a familiar looking expression here that the output is equal to a transfer function, which is made up by the transfer function open loop on top divided by 1 plus the open loop on the bottom, this being our closed loop transfer function GCL, all times our input, our reference angle there of theta r. So therefore our closed loop transfer function GC is the open loop transfer function, that's 3 Kc divided by s times s plus 6 divided by 1 plus the same thing here, 3Kc divided by s plus 6. So I multiply the top and bottom by s times s plus 6, and I end up with 3 Kc on the top. On the bottom I get an s squared plus 6s plus 3 Kc. As that, and I'll write that as a numerator in Cl, which is really a constant, divided by the denominator dCl like this. So the important thing that we've learned about transfer functions, whether they be for controls or whatever, is that the response, a lot of information on response, whether it be free or forced, comes from knowing our poles. So our denominator dCl, which is s squared plus 6s plus 3Kc, when that's equal to a 0, we get our poles. This is what for second order systems becomes called omega n squared, and the 6 here is in our standard form is 2 zeta omega n. So therefore from this we see that the natural frequency omega n, that's just the square root of 3kc. We see that 2 zeta omega n, that's equal to this constant number of 6. So zeta omega n itself is equal to 3. And zeta, which is 3, therefore 3 divided by omega n, which is the square root of 3 over kc, is that. So all this here is coming from just looking at the standard form of our denominator d of our transfer function. In order to find the poles, though, p1 and 2, there are two of them, is minus 6 plus or minus 6 squared minus 4 times 3kc divided by 2. So this becomes minus 3 plus or minus 9 minus 3kc. So these are our two poles. It's pretty important to look at these in the complex plane because that's really going to help us out here. And in a subsequent example we're going to do on design. So if we can understand how the poles move around in the complex plane, it's going to give us some insight on how we can design our system. So this here is going to be real part of our poles on this axis, imaginary on this one here. So if we look back at our roots or poles here, P1, 2, we see that when Kc is a 0, we have one pole here at the origin and we have one pole over here at minus 6. As you increase Kc in a positive way, what happens there is this pole on the left moves to the right, and the pole on the right moves to the left. Where they hit each other is going to be where the real part is minus 3. When they hit each other, they split, and one goes up and one goes down. Straight lines. Okay, and this happens when Kc is equal to 3. Okay, how do I know that it's a straight line once they hit? Well, once they hit, then if we look back at our characteristic equation, let me maybe write that down in a different way. We know that in our standard form this becomes minus zeta omega n plus or minus the square root of omega n square root of zeta squared minus 1. Where they hit is when zeta is a 1. So when zeta is less than 1, the roots become complex. So this becomes the real part of the poles for the damping ratio less than 1. And so you see that this here is independent of Kc. That is, once you're over in the underdamped range, that real part doesn't change. So one goes up and one goes down in terms of the imaginary part. So the real part remains unchanged. So that's going to help us out, I think, later on when we talk about design. Okay, let's get the answer. We saw from above that zeta was equal to square root of 3 over Kc. Kc was 16 thirds. So this is the square root of 9/16. So the damping ratio is 0.75, and as we suspect it from our plot above, this would correspond to an underdamped case. We recall that for the underdamped case we have a true second order response, so Ts is 4 times the time constant. Time constant is 1 over zeta omega n. So from above we saw that zeta omega n is always equal to 3, so that's 4/3. And since it's underdamped, we need to be concerned about percent maximum overshoot. So that ended up being 100 times the exponential of minus pi zeta divided by the square root of 1 minus zeta squared. We put zeta equal to 0.75 in there, which we found from above, and we find out that the percent overshoot for a step input is a little bit more than 2.8%. So this is analysis. We're given parameters. We want to know something about the response. The settling time is 4/3 of a second. The percent overshoot is around 2.8%.